I'm James. I'm an engineer on the Go agent team at Contrast Security. I'm here to show you how Contrast Assess helps you keep your Go application secure. This is a demo aimed at Go developers and operators, so we're going to be getting a little technical. I want to start off by talking a little bit about what Contrast Assess is. Assess is an interactive application security testing analyzer. This means that we embed monitoring into your running software and extract and analyze security relevant information. That might sound a bit abstract, but there's a good chance that you've been using a tool that takes advantage of this general strategy already. Go's built-in race detector is using the same approach, where they're using it to analyze synchronization and we use it to analyze security. This gives both tools highly accurate results and low false positive rates. You also don't need to be or hire a pen tester to get results here. Just like the race detector finds concurrent map writes, even when the runtime doesn't panic, Assess will find vulnerabilities even when they aren't being exploited. You just need to send requests to the app. This can be done with end-to-end tests or in a QA environment that's manually tested. You can also run everything locally for small apps or when you're investigating specific issues, and that's what I'm going to be doing. So for this demo, I'm going to be using Go Test Bench, which is an intentionally vulnerable Go app. There's two versions of the test bench available, one built using the standard library, just NetHTTP, and the other one which uses the Gin framework for the backend. These are the two frameworks that the Go agent currently supports for Contrast Assess, but we're instrumenting NetHTTP, so we're able to find vulnerabilities in most other frameworks as well, just not the full feature set. Once we have our app, we now want to download and install the agent. So I'm here in the Contrast UI, and I'm going to click on Add New. We want the Go agent, and there's two things that we need to get here. First, we're going to download our Contrast Security YAML file, and we're going to place it in the working directory. This file contains our auth credentials and configures reporting to Contrast. There are other configurations as well, but we're fine with just the defaults. The second thing we're going to do is download and install the agent itself. I'm running on a Mac, so I would go through the direct download process, and this is just downloading an executable, granting it permissions, and adding it to our path. I'm going to move over to the project. You can see that I have the Contrast Security YAML file as well as Contrast Go installed. Now, Contrast Go provides the same API as the Go tool. So if you would normally build your app with a command like this, we're now going to use Contrast Go in place of Go. What this is doing is it's injecting instrumentation into the source code files and then passing those rewritten files onto the Go toolchain. And for that reason, we support the two latest Go releases, which is the same as the Go team. Now that we've built our instrumented app, let's spin it up and find some vulnerabilities. I'm going to start with path traversal. Path traversal is a vulnerability that allows users to access files outside of the directory that the application is currently running in. A classic example of the file that you might access would be the Etsy pass. We're going to try to access a demo file right alongside it. And you can see here that we can, so the endpoint is vulnerable to path traversal. And if we switch over to the application view in the Contrast UI, we see that the vulnerability is correctly reported. We can click on the vulnerability to view some more information about what's going on. In the overview, we see that the input query string param was used to open the file. And in the details, we can see a little bit more Go-specific information about what function calls were actually being used. This is a pretty small vulnerability. There's not much to the trace. So I'm also going to show something that's a bit more complicated, and that would be SQL injection. So SQL injection scenario, your application requires authentication. users pass credentials in through the headers, and then you use those credentials to construct a SQL statement that verifies that the username and the password match. We're going to try passing in Bobby Drop Tables as the username. If we go back to the UI, we can see that a SQL injection vulnerability was reported, as well as a cross-site scripting vulnerability. That was a bit unexpected, so let's see if we can verify it. Sure enough, there is reflected XSS in this endpoint. The SQL injection vulnerability is marked as critical though, so we should try to fix that as soon as possible. If we look into the details, we can see an overview of the data flow and how we go from user data to the actual injection site. First, we pull the credentials from the headers. Then we convert the credentials from a string to a byte slice. We unmarshal that byte slice into a struct and print the fields of the struct into a SQL statement that we finally execute against the database. We can click on How to Fix to see how to fix this vulnerability. There are two options presented. The first is to use an ORM, but we'd like to keep our dependencies minimal since this is supposed to be a standard library example. The second option shows that we can replace SQL queries that were constructed with just string concatenation with the preferred parameterized query, which will be safe. We saw in the details here that the query was being constructed with strings and not parameterization. So I think that this is a good approach. We can also see here exactly where this line occurs. SQLinjection.go, line 50. So if we switch back to the project, open up SQLinjection.go here, and on line 50, we can see the line of code as presented in the UI. To switch this to parameterization, we'd replace the %s formatters with question marks, and then pass user input and test as variadic arguments at the end of the string. This is actually the same as the code being used below. So we can just update the code to fall through to that case. Now that we think we know what the issue was, I'm going to mark the vulnerability as fixed. If we switch back to the Vulnerabilities tab, we see that the SQL injection is no longer listed as a vulnerability. We're now going to rebuild the app, hit the endpoint again, and verify that the vulnerability doesn't appear. This time I'm using contrast go run to skip the intermediate step of the executable. So it's up and running. We hit it, and if we refresh our vulnerabilities, we see that there's still no SQL injection. So we can remediate the vulnerabilities that we found, but that's sort of like making sure that our tests are passing. We still don't really know that everything's been tested though, and for that, there's route coverage. Route coverage with contrast assess shows all of the routes that are currently listening for your application, as well as which ones have actually been exercised. You can see here that there are a number of routes that look like they may have vulnerabilities that we haven't exercised. Once all of the routes that have been discovered have been exercised, and you've fixed all of the vulnerabilities found, you can be confident that your application is secure. That concludes the demo. If you'd like to learn more, visit contrastsecurity.dev.